and I'll be demonstrating my implementation of the tic-tac-toe game, the Max-Min strategy, the week 3 project for the computer science for engineers at Full Sail University. As you can see here, I have the application up, and one of the requirements is that we need to have 3 screens out here. This initial screen counts as one. As you can see, we have all of our different menu options that we have available for the user. The player versus player, the player versus the computer, computer versus computer, the difficulty levels, and the credits. So as you can see, I select on the credits. This is me, this is the class, and this is when I started working on the Android part of the project. I also implemented difficulty levels. So the original requirement was to specifically implement the min-max algorithm, which we represent here as the difficult level, as well as the randomization, which is basically the easy level. I also implemented a hard level, mostly from the perspective that I didn't quite completely get the difficulty min-max logic working, but I was pretty darn close, so that actually feeds quite nicely into a middle level. It's almost exactly min-max, but not completely there. So I just basically made that a feature by mistake. The difficulty level we're going to put to expert and then demonstrate that this functionality actually works using computer versus computer mode. So in computer versus computer mode, the algorithm is playing as both players out there, and as a part of that process, what you can see is it's always going to try to drive the very first play to the center of the screen. And the reason why this is the logic that I use to implement calculating where the next move should be is I ran through multiple processes of trying to figure out should I use recursion? How do I use recursion to go calculate this? And basically I spent a lot of time actually looking at the game board and mapping it out. And as a part of that mapping out process, what I did is to determine for each cell how many possible ways can I win. And so when the game actually starts out and there's no pieces actually on the board, what you'll find is going from left to right and working down, I get a pattern of 757, 595, 757. So each one of those numbers represents, for example, if I'm here, I can basically win going 1, 2, 3, 4, 5, 6, 7. Now, what's interesting about this is when you look at the center cell, there's actually 9 possible ways that you can win: vertically, horizontally, and diagonally in both directions. So if you are the first player, or at any point in time that center cell early in the game is available, that you want to put your piece into that cell, because that increases the probability of you winning the game from that perspective. And so that's why you will see that the logic for this actually leverages the fact that the very first thing we want to do when we make a move after we've initialized everything is to go and put our piece into that cell one by one if it's not occupied. So, based off of that, this is the logic that we leverage to try to identify where the best place is to go each time. The way that this logic is broken down is I define three maps. The first map is basically what I was describing, the mathematical computations based off of, at that point in time in the game, for each one of the cells. What is the number of possible cells that are available for me for that location? So if a cell is occupied either by my piece or another piece, it gets a value of 0. However, if a cell, for example, is not occupied, but both of the cells on the left and the right, so a middle cell but not the center, then we basically don't count them. And we also only count the cells in the directions that you can actually win. So if it's a center top cell, so in the case that it's up here, we basically are only calculating in these cells and these cells. But any cells that are already occupied, either by ours or somebody else's, don't get included. So as the game progresses, the values of this matrix go down based off of that. In the case of the winning move map, what we needed was a map that would go and calculate effectively how many moves I have left in a particular cell for me to win. And so what I'm really interested in this calculation is if there's if there's a cell that has a winning move map of 1, then that is the cell that I want to do on my next move, because that means I'm going to win the game. Now, interestingly enough, is we take that exact same logic and we flip it on its head and we say, okay, I want a opposing winning move map. So is there one move that my competitor can do and they will win the game? And so what you will see is the logic that we implement, other than taking the center cell, but the very next thing that we want to do is check to see, can our opponent win in one move? Because if they can, we need to block that cell, and that's what this does. The very next thing we do is, can we win in one move? Because if that's the case, then we want to do that. And then the remainder of this code is basically taking the information from the best move map and determining, based off of the numbers that we calculate in that process, where's the best heavy weighted, highest value location to go and put our piece. Now, in most of this, in most of the calculations here, you will find that there are multiple returns that come back. However, I take the first one out of the list. In the process of playing the game, as you can see, as we went through the process here, we also generated music or tones from this perspective. So this was one of the enhancements that I applied to the game process, and that logic was done inside of here. Oops. So we just took a recording, that little magical tone, added it as a part of the project. We got context, we got reference to the audio, and then we tell the media player to go play that. And then based off of that, we play it after each move is selected. Again, we had to do 3 different screens. So as you can see, we have a screen here that determines who's won or who's lost, and then also provides the ability to select play again in the process. Okay, so I'm now going to switch gears and prove out. Let me just first show that our dialog boxes are working for credit. Player versus player, we can now choose to play against ourselves. So in the manual mode, I utilize this as a means to troubleshoot all of the graphics part and make sure that that was working successfully. And then also to work out my logic to determine when I could show a graphic and determine when the game would come to an end. And as you can see, that's working successfully as well. So now I'm going to switch gears to player versus player. And we are playing on the highest difficulty level. And as you can see, computer is definitely not going to let me win. So now I will drop down as part of my enhancements. I provided 3 levels, as I mentioned. So I'm going to switch down to an easy level, and in this case the computer basically just randomly selects where it's going to put its code. So coming back to my code, just a couple of things here. Switching over to the easy level. So my logic for the easy level, I put in a separate class here. And as you can see, all we're doing is just basically using randomization to decide where the next place is from that perspective. I also implemented hard, and I did this by accident. Originally, I was really struggling to figure out how to get the min-max to work. I was very, very close, and instead of throwing away that code, I basically decided, you know what, we'll just leave this as the hard level. And so this is really a good intermediate middle level because it's pretty close, but then it does some weird things in the middle of the process. And so that's what makes up our middle level of the code.